let's look at this integral. Integration from 0 to 1 log x raised to the power n dx. Okay, so yeah, let's look at the integrand. Now since n is a positive integer, the continuity of log x is preserved. So let's simply check the continuity of the integrand of log x in the given interval. Okay, here's 0 and this point is 1 comma 0, and this is y equals log x, x-axis, y-axis, and the y-axis is the vertical asymptote of the curve of y equal to log x. So in this interval right here, we have a point of discontinuity, which is the point x equals to 0. So we can write r tends to 0 from plus r to 1 log x raised to the power n dx. Okay, let's not put an equal to sign right away right here. We're gonna check the convergence, check the convergence using this limit. This is an improper integral. Okay, this is an improper integral. We're checking its convergence. We're not evaluating it right away. What we are doing right now is checking the convergence. Alright, okay. So if this limit exists, then we say that this integral is convergent, and if this reduces to some value k, then the value of this integral will be equal to k. Alright, we're using the definition of an improper integral. So now let's simply make a substitution. Okay, let's make the substitution u equals to log x. Then the lower limit will be log r, and the upper limit will be log 1, which is 0. This will be u raised to the power n, and we're going to use the new variable du. For this, we need to evaluate the derivative of u with respect to x, and we have 1 over x right here. So the substitution factor is 1 over x, and we need to divide the integrand using the substitution factor like this. So this is u equals log r and u equals 0. Now 1 over 1 by x means simply x, and x equals to, from this particular substitution, we can write x equals e raised to the power u. So since this is x, we can write it as e raised to the power u. So this reduces to something like log r 0 un e raised to the power u du. Okay, something like this. Okay, this is it. So now if we look at the integrand carefully, we can compare it with the gamma integral. Alright, we can compare it with the gamma integral. Gamma integral will be something like this, and this will be convergent for any positive real number. Alright, now let's see. This limit is around minus infinity, this limit is 0 as it is, and we have u over here. We have u over here. Alright, we have u over here. We just need something else, and we're going to use the something else over here as well. Okay, now let's see if the substitution u equals to minus y makes any kind of sense or not. Now from this integral, let's see, from this integral, now r tends to 0, right? R tends to 0. R tends to 0 from plus, so it is okay to take r to be less than 1 since we are making it close to 0. Making it go closer and closer to 0. Let's take r less than 1. Alright, r less than 1. Nothing wrong with that. So log r would be less than 0, as you can see here. If r is somewhere over here, then the logarithm is 0, less than 0, sorry, and therefore the value of u is between log r and 0, so it's taking non-positive values only. The variable u is taking non-positive values only. So if we then, since these are taking non-positive values, we can write u to be equal to minus y, where y is a non-negative variable. Alright, y is a non-negative value. So let's make the substitution y equals minus u. Okay, y equals minus u, then the substitution factor will be minus 1, and what are we going to get? The upper limit, the lower limit will be minus log r, the upper limit will be 0. This will change to, since u equals minus u equals minus y, this changes to something like this, and we're going to use dy, so we need to divide the integrand by minus 1, which will give us simply minus 1. Okay, this is what we are going to get. Now we're going to remove this minus, and interchange the limits of integration. Alright, limit r tends to 0 from plus 0 to log r. This will give us minus 1 raised to the power n, y raised to the power n, e raised to the power minus y dy. Now since this thing is independent of y, it will come out of the integral, and since this is also independent of r, it will come out of the limit. So we have minus 1 raised to the power n, limit r tends to 0 from plus 0 minus log r, e raised to the power minus x, x raised to the power n dx. Just replacing the variable y with x because it's a dummy variable. Alright, now let's see. Do we have a gamma integral right away? No. But do we have the integrand of the gamma integral? Yes, we do have it. So let's evaluate the corresponding gamma integral. Okay, e raised to the power minus x, x raised to the power n dx. This can be written as 0 to infinity e raised to the power minus x, x raised to the power n minus n plus 1 minus 1 dx. So since we got n plus 1 instead of s, this will be equal to gamma n plus 1. Alright, gamma n plus 1. So yeah, what are we? Yeah. N is a positive integer. So by property of gamma integrals, if n is a the n is a natural number, then we can write gamma n plus 1 as n factorial. Alright, n factorial. In general, gamma s plus 1 can be written as s gamma s for s plus 1 greater than 0. Alright, this is the general expression, and if s is a natural number n, then this will be the corresponding result. Okay, so let's see, this is convergent, right? This is convergent. This will always be convergent for any natural number n in particular. So we can write it as limit, let's say r tends to infinity 0 to r e raised to the power minus x, x raised to the power n dx. Alright, or even more conveniently, we just need to make this upper limit tend to infinity. Okay, this upper limit tend to infinity. So instead of using this one, it will be more appropriate if we use this thing right here. Limit r tends to 0 from plus 0 minus log r x n e raised to the power minus x dx. Why? Because as r tends to 0 from plus, this will tend to minus infinity, as you have seen from the graph, and since we have the negative sign, log r minus log r will tend to plus infinity as r tends to 0 from plus. So we can write this integral as this limit. Alright, we can write this integral as this limit, and therefore this will simplify to minus 1 raised to the power n limit, no, not the limit, minus 1 times the gamma integral 0 to infinity x to the power n e raised to the power minus x dx. Now this was found to be equal to the factorial of n, so we can write factorial of n like this. Okay, and therefore, as in the conclusion, what we can say is 0 to 1 log x n dx is equal to minus 1 raised to the power n times the factorial of n for every n belonging to z plus. Okay, yeah. Now if we have n to be some earlier integers, the smaller integers like n raised to the power log x raised to the power cube or fourth power or something like that, then we can, oh yes, I got him, then we can use the substitution u equals e raised to the power x and evaluate this thing right here. Let's call this in. Let's call in to be the indefinite integral log x raised to the power n dx. Let's use u is equal to log x, so that x is equal to e raised to the power u, and we get u raised to the power n du. Derivative would give us 1 over x, so x means e raised to the power u. Now yeah, first function, integral of second minus derivative of first times the integral of second, which means un e raised to the power u minus n I n minus 1. This is the reduction formula which we can use for smaller values of n. Now if we start using this, you're gonna have to use limits as well. Okay, you cannot get away with the limits, but yeah, if we want to use this for larger values of n, it will take a lot of time, so I suggest you to use gamma functions or gamma integrals. Okay, all right, that's it for now. Thank you very much.